A policyholder, i.e. Murphy, initiates a call to inquire about hail damage coverage. The policyholder also seeks clarification on the policy's excess deductible amount. The call center agent is tasked with providing accurate policy details. The agent navigates multiple computer screens to locate the relevant policy information. An insurance agent reviews policy endorsements on their computer. The agent examines a PDF document detailing the endorsement terms. A free text note indicates specific coverage details, such as hail included. The agent consults a database table to verify coverage parameters. Database fields include Boolean flags for coverage and numeric values for deductibles. The insurance policy has been modified. A midterm deductible adjustment was implemented last year. This adjustment altered the amount the policyholder pays out of pocket before insurance coverage begins. The policy was upgraded to a higher exposure class in its current version. This upgrade reflects an increased level of risk associated with the insured asset or activity. Policyholders should be aware of these changes. Financial processes require precise details to ensure accurate claim assessments. Exact limits of coverage must be identified to determine the maximum payable amount. Deductibles, which are the amounts the insured pays out of pocket, must be verified. Exclusions, specifying what is not covered, need to be clearly defined. The validity of these details is crucial as of the date of the loss, not the current date. Using the correct date ensures that the policy terms in effect at the time of the incident are applied. Legal departments require a comprehensive record of coverage terms. This record must include a history of all changes made to the coverage. An auditable history ensures compliance and accountability. This audit trail supports legal defensibility and informed decision-making. Data science applications often require a well-defined peril taxonomy. A peril taxonomy is a structured classification of potential risks or hazards. This taxonomy is essential for powering accurate and relevant recommendations. For example, it helps identify similar perils based on shared characteristics. Sleet can be identified as a similar peril to hail through a comprehensive taxonomy. This enables more effective risk assessment and mitigation strategies. The central challenge is to accurately model insurance coverage in a database system. This involves distinctly representing perils, coverage inclusions, and specific coverage terms. Each element must be correctly linked to the appropriate policy version. Furthermore, these components need to be associated with the relevant risk object being insured. The objective is to design a database that supports specific, detailed queries. An example query seeks to identify the peril matching hail for a specific claim and date. The query also checks if the peril is included and determines the applicable terms. The system should return a single, deterministic answer for each query. Effective database design eliminates the need for manual data retrieval. It streamlines the process of determining data coverage. This is achieved by organizing data in a structured and accessible manner. Well-designed databases reduce reliance on scattered notes and documents. This leads to improved efficiency and accuracy in data management. A naive approach to database design involves creating a single table to store all coverage information. This table, named Coverage Naive, includes columns for each type of peril, such as hail and flood. Each peril column stores information about whether coverage is provided for that specific peril. Additionally, columns are included to store the deductible amount for each corresponding peril. This design results in a wide table with numerous columns, potentially leading to inefficiencies. The coverage, naive table structure is a simple but often suboptimal method for organizing coverage data. A poor database design can lead to the addition of new columns for each new peril. Adding columns for each new peril breaks historical data integrity. This approach causes query complexity to increase exponentially. The increasing query complexity results in unmanageable spaghetti code. Varying deductibles across versions further complicate the code and database structure. Hard coding involves embedding fixed data directly into the source code of a program. This means the data is part of the code itself, rather than being obtained from external sources. For example, a rule might be hard-coded to include coverage if the peril is hail or sleet. Another hard-coded rule might set a fixed deductible amount, such as $250. Hard-coding makes the code less flexible and harder to update, as changes require modifying the code directly. Modifying deductibles in a poorly designed database can lead to significant issues. A worst-case scenario involves the need for complete redeployment of the system. This can result in audit failures due to inconsistencies in the data. Bugs may also arise, causing claims to be mispriced without any immediate indication. A novice database designer starts with free text notes as the primary data source. The designer creates a table named Coverage Note to store these notes. The coverage note table includes a note column. The note column contains free text information. Example notes include details like hail covered up to Euro 3K, €250 excess. This unstructured approach can lead to data inconsistency and difficulty in querying. Using NLP guesswork instead of concrete facts can lead to significant issues in database design. One major problem is the introduction of ambiguity, making data interpretation unclear. This ambiguity can cause disputes among users regarding the meaning and validity of the data. Furthermore, reliance on NLP may result in data leakage, compromising sensitive information. Ultimately, these issues can lead to fines and legal repercussions due to non-compliance with data regulations. A common database design error involves combining peril and coverage into a single table. This collapsing of tables results in the loss of crucial hierarchical relationships. Specifically, inheritance structures, such as hail belonging under severe weather, are compromised. The absence of this hierarchy prevents effective roll-up queries. Consequently, the database's ability to aggregate and analyze data across different levels of coverage is significantly impaired. A common database design error involves misinterpreting 0 divisé par 1 versus 0 divisé par many relationships. This often occurs when modeling terms like limit or deductible. Designers may incorrectly assume that only one term can exist. In reality, multiple terms can often coexist, requiring a 0 divided by many relationship. A common database design mistake involves directly overwriting a running used limit column. This often occurs due to flawed accumulation logic within the database. Instead of overwriting, a more robust approach is recommended. Derive year-to-date (YTD) and quarter-to-date (QTD) usage dynamically. This derivation should be based on atomic claims data. Join the claims paid data with the relevant coverage information to accurately calculate usage. Coverage represents the authorization to provide payment for insured losses. This permission is dictated by specific perils outlined in the insurance policy. The terms and conditions within the policy further govern the scope of coverage. Coverage is effective as defined within the specific version of the insurance policy. In database design for insurance, it's crucial to distinguish between perils and coverages. A peril refers to the cause of a potential loss, categorized within a taxonomy. For example, hail is classified under the broader category of severe weather. Understanding this taxonomy is essential for accurate risk assessment and policy management. Coverage in database design refers to the inclusion of specific perils within an insurance policy. It specifies whether a particular risk is covered under a given policy version. The concept of coverage is relevant to specific risk objects. A risk object is any item or entity that is potentially subject to a peril. The database design must clearly indicate which perils are covered for each risk object. This ensures accurate and comprehensive policy information within the database. Database design incorporates terms as rows to manage multiple conditions simultaneously. Each row represents a specific term, such as deductible, limit, or exclusion. This structure allows for defining various terms at once, like an overall limit combined with a per-incident deductible. The row-based approach ensures flexibility in handling diverse and layered insurance terms. Row-based coverage ensures adaptability in database design. New perils can be accommodated without altering the database schema. The addition of new term types also avoids schema modifications. Instead of schema changes, only data updates are required. This approach enhances the flexibility and maintainability of the database. Database rules are stored within tables for structured management. These rules are designed to be auditable, ensuring transparency and accountability. Version control is implemented to track changes and maintain a history of rule modifications. Endorsements of rules lead to the creation of new policy versions. This endorsement process avoids overriding existing policies, preserving historical data. Database design should prioritize clarity and understandability. Notes and comments should serve as explanations, not replacements for clear design. The database structure itself should be self-explanatory where possible. Well-named tables and columns enhance readability. Relationships between tables should be clearly defined and easily understood. Documentation should supplement, not substitute, a well-designed database. Strict normalization is a database design approach focused on minimizing data redundancy. This approach often involves creating multiple tables to represent different entities and their relationships. One key table is peril, designed to be self-recursive, possibly to represent hierarchical peril relationships. Another table, coverage, links policy versions to specific perils and risk objects. The coverage table establishes which perils are covered under a particular policy. A coverage, Term table specifies the terms of the coverage, including term type, amount, and currency. Strict database normalization offers advantages in auditability. Normalization enhances composability within the database structure. However, strict normalization often leads to a greater number of join operations. Increased join operations can potentially impact query performance and complexity. This database design option focuses on normalization and utilizes rule templates. Coverage templates are added, organized by product and line of business, LOB. These templates define the structure and rules for different coverage types. The coverage templates are then instantiated to create specific policy versions. This process ensures consistency and standardization across various policy offerings. Normalized database design involves organizing data to reduce redundancy and improve data integrity. One advantage of normalized databases with rule templates is faster onboarding for new users. The use of rule templates also minimizes errors during data entry and manipulation. However, a disadvantage is the potential for template drift over time. Template drift necessitates ongoing management and updates to maintain data consistency. Effective management of rule templates is crucial for the long-term success of normalized database design. The Rules Engine hybrid approach combines normalized data storage with rule-based evaluation. Normalized facts are stored in the database following standard normalization principles. A rules engine is employed to manage and evaluate complex dependencies between data elements. The rules engine applies predefined rules to the stored facts. This allows for dynamic decision-making and inference based on the current state of the data. This hybrid model is suitable for applications requiring both data integrity and flexible rule-based logic. Rules Engine Hybrid offers expressive capabilities in database design. This approach allows for complex logic and decision-making within the database. However, Rules Engine Hybrid can result in heavier operational overhead. The increased complexity may impact performance and resource utilization. Option 2 zur Database Design prioritizes normalized data integrity. Normalization ensures data consistency and reduces redundancy. This option also focuses on accelerating data issuance. Acceleration is achieved through the use of templates. Templates facilitate rapid instantiation of data structures. A fast and consistent rollout is optimal across various scenarios. Minor variations should be managed as specific data entries. This approach avoids modifying the core code for every small change. Data-driven variations enhance maintainability and deployment speed. A SQL table named Peril is created to store peril-related data. The Peril table includes columns such as Peril, ID, Name, and Parent, Peril, ID. The Peril ID column is defined as a big serial primary key, ensuring unique identification of each peril. A foreign key constraint links parent, peril, ID to peril, ID, establishing a hierarchical relationship between perils. A coverage table is created to store coverage information. Coverage, ID, is the primary key, automatically generated and unique. Policy, version, ID, and peril, ID are foreign keys referencing other tables. Risk, object, ID is a foreign key that can be coverage. Code specifies the type of coverage, and is included indicates if the coverage is active. A coverage term table is created to store details about coverage terms. Coverage term ID is the primary key. A big serial automatically incrementing. Coverage ID is a foreign key referencing the coverage table. Term type specifies the type of term, limited to limit, deductible, or exclusion. Amount is a numeric field representing the term's value, with a precision of 18 and scale of 2. An index is created on the coverage ID column to improve query performance. A coverage template table is created using SQL. Template ID is defined as a big serial primary key. Product, ID, and peril ID are defined as big integers and foreign keys referencing product and peril tables respectively. Is included as a Boolean field with a default value of true. The SQL code creates a table named coverage, template, term. Template, term, ID is a big serial primary key, automatically incrementing. Template, ID is a big integer, acting as a foreign key referencing coverage, template. Term type is text, restricted to limit, deductible, or exclusion. Amount is a numeric field with a precision of 18 and scale of 2. Currency is a character field of length 3, likely for currency codes. The SQL query retrieves hail coverage details for a specific policy. It identifies the hail peril and selects relevant coverage information. The query joins policy versions, coverage details, and coverage terms to filter the results. It returns whether hail coverage is included and the deductible amount for policy POLIE0001 as of the 1st of February 2025. The SQL query performs a roll-up of coverage data based on the severe weather peril parent. A recursive common table expression, CTE named tree, is defined to traverse the peril hierarchy. The CTE starts with the severe weather peril and recursively joins with the peril table to find all child perils. The main query selects the count of coverages where the peril ID is in the set of IDs returned by the tree CTE. Effectively, the query counts all coverages associated with severe weather and all of its subperils. This presentation outlines 3 examples of poor AI data design practices. These examples serve as cautionary tales for AI development. Understanding these pitfalls is crucial for creating effective AI systems. Avoiding these mistakes can significantly improve AI performance and reliability. The following captions will detail these 3 flawed data design approaches. A database table named coverage, note, is being created. The table includes a column named policy, version, ID of integer type. It also contains a column named note of text type. The note column stores textual information. Example notes include details like hail covered up to Euro 3K, 250 euros excess. Training AI with handwritten notes can lead to unpredictable model behavior. The AI may learn to interpret slang and generate illogical policy. This can result in the AI hallucinating policy logic, making it difficult to audit. The outcome is random approvals and unreliable decision-making processes. AI models can learn from data containing opinions. The model's training focuses on recognizing and replicating patterns in subjective viewpoints. The AI is designed to identify and understand sentiments expressed in the data. The model does not learn objective policy facts. The AI is trained to understand and generate opinionated content. A SQL table named coverage, features, is created to store insurance policy data. The table includes a policy, ID, column, which is an integer. Boolean columns, hail, flood, fire, wind, represent different types of coverage. A true value in these columns indicates that the policy covers the specified peril. This structure allows for efficient querying and analysis of coverage types per policy. A worst-case scenario involves the need to rebuild data pipelines for each new peril. Models may crash when exposed to new and unforeseen perils. Retraining models and redeploying dashboards becomes a constant requirement. Feature explosion can transform maintenance into an unmanageable task. Businesses can experience operational disruptions during extreme weather events. These disruptions can be attributed to limitations in AI-driven analytics systems. Specifically, analytics platforms may struggle to process novel weather-related terminology. The inability to recognize new weather terms hinders accurate data interpretation. This leads to a temporary freeze in analytical capabilities. Consequently, businesses face challenges in adapting to and managing the impact of storms. The SQL update statement modifies existing records in a table. The UP-date coverage clause specifies the table to be updated, which is coverage in this case. The SET used limit YTD equals used limit YTD plus 1000 clause updates the used limit YTD column. The existing value of used limit YTD is incremented by 1000. The where coverage ID equals 1 clause filters the update to only the row where coverage ID is 1. Overwriting year-to-date YTD or quarter-to-date QTD totals represents a critical data integrity issue. This action destroys the historical accuracy of the data. Consequently, AI features that rely on this data become unreliable and produce nonsensical results. Fraud detection systems will flag incorrect patterns, leading to false positives or misdetections. Auditors will be unable to verify past data usage, compromising accountability and regulatory compliance. AI models generate predictions based on patterns in the data they are trained on. These predictions may not always align with factual accuracy. The model essentially predicts on ghosts, meaning it relies on learned associations rather than concrete facts. This can lead to outputs that are statistically probable but factually incorrect. Therefore, AI outputs should be critically evaluated for accuracy and not blindly accepted as truth. This AI design approach uses LLM divided by NLP to infer coverage divided by deductible information directly from free text notes. The system attempts to extract rules by analyzing textual notes. However, this method has several critical limitations. It is considered fragile, meaning it is easily disrupted by variations in note-taking styles. The process is non-deterministic, leading to inconsistent results for similar inputs. Finally, the system lacks auditability, making it difficult to trace the reasoning behind its decisions. One-hot encoding is used to create machine learning features from peril columns like hail, flood, and fire. Each peril category becomes a binary feature, indicating presence or absence. Applying one-hot encoding to dozens of peril columns significantly increases the dimensionality of the dataset. This dimensionality explosion can lead to computational challenges and overfitting. A major drawback is the inflexibility when new, previously unseen perils emerge. The model is not designed to handle new peril categories, requiring retraining and code modifications. The current system overwrites running totals, specifically used, limit, YTD, directly on coverage data. This in-place updating of data introduces significant data leakage issues. Overwriting totals leads to reconciliation nightmares, making data verification extremely difficult. The practice of overwriting directly impacts the accuracy of YTD, year-to-date, features. QTD, quarter-to-date, features are also negatively affected by this overwriting approach. The core issue is the lack of proper data versioning and historical tracking of used, limit, YTD. A well-designed, normalized database structure provides significant advantages for AI applications. Normalization reduces data redundancy, ensuring consistency and accuracy. This improved data quality directly enhances the performance of AI models. A structured database simplifies data retrieval and processing for AI algorithms. Efficient data management reduces computational costs and training times for AI systems. Normalized databases facilitate better feature engineering, leading to more effective AI solutions. Database normalization organizes data to minimize redundancy and improve data integrity. A normalized structure facilitates the extraction of relevant features for machine learning. Well-organized data enhances the efficiency and accuracy of machine learning models. Normalization ensures data consistency, which is crucial for reliable machine learning outcomes. A normalized database structure enhances data management. It provides a transparent history of policy modifications. All changes to coverages are clearly auditable. This ensures accountability and traceability. It supports efficient tracking of policy evolution. Database normalization is a crucial process in database design. It structures data to minimize redundancy and improve data integrity. A normalized structure ensures data consistency across the database. Accurate and consistent data is critical for reliable AI predictions and analysis. Therefore, normalization supports the effectiveness of AI applications that rely on the database. A normalized database structure is designed for scalability. Scalability allows the database to easily adapt to increased data volume or complexity. The normalized structure can readily incorporate new perils. It also accommodates new coverage terms without requiring significant redesign. Templates streamline the integration of new policies and coverages. This acceleration is achieved through pre-designed structures. These structures offer a standardized framework. The framework ensures consistency and efficiency in database design. Data governance policies are essential for maintaining data quality. These policies ensure consistency across all datasets. Effective governance leads to more reliable data analysis. Consiste data improve decision-making process. Database data can be leveraged to train AI models. These AI models can be applied to various use cases. One such use case is fraud detection, where AI identifies suspicious transactions. Another application is risk assessment, where AI predicts potential risks. A well-designed data infrastructure is crucial for AI applications. This is especially true within the insurance industry. Effective data design ensures data quality and accessibility. High-quality data is essential for training accurate AI models. Accessible data allows for efficient AI deployment and usage. Therefore, prioritizing data infrastructure is key for successful AI implementation. Database design must prioritize seamless integration capabilities. This ensures compatibility with various other systems. The design should also facilitate easy incorporation of diverse data sources. This promotes a unified and comprehensive data ecosystem. Database design must accommodate evolving business requirements. Flexibility ensures the database remains relevant and efficient. Adaptability reduces the need for costly redesigns later. A flexible design supports new data types and relationships. It also allows for the integration of new technologies. Scalability is a key aspect of database design flexibility. Database design must prioritize security to protect sensitive information. Security measures should be integrated throughout the database design process. Data protection is a critical aspect of database integrity and compliance. Secure database design helps prevent unauthorized access and data breaches. Database design should prioritize cost-effectiveness in both implementation and maintenance. A cost-effective design minimize initial development expense. It also ensures lower long-term operational and maintenance costs. This approach maximizes the return on investment for the database system. Cloud-based data warehouses are used for storing insurance data. These warehouses facilitate efficient processing of large datasets. Cloud solutions offer scalability and cost-effectiveness. This leads to improved data analysis and decision-making. Data visualization tools are crucial for exploring insurance data effectively. These tools enable analysts to identify patterns and trends within the data. Visual representations simplify complex datasets for easier understanding. Interactive dashboards allow users to dynamically filter and analyze information. Common visualization types include charts, graphs, and heat maps. Effective data visualization supports better decision-making in the insurance industry. Database design plays a crucial role in enhancing customer service and satisfaction. Well-structured data enables efficient retrieval of customer information. This allows service representatives to quickly address customer inquiries. Improved data access leads to faster resolution of customer issues. Ultimately, effective database design contributes to higher customer satisfaction levels. Data plays a crucial role in informing and guiding business strategies. Effective database design is essential for leveraging data assets. A well-structured database ensures data accuracy and reliability. Businesses can gain insights into market trends and customer behavior. Data-driven insights enable better resource allocation and investment decisions. Ultimately, data empowers businesses to make informed choices and achieve strategic goals. AI is poised to revolutionize the insurance industry. AI's potential impact is transformative. AI is set to redefine core insurance operations. This transformation spans underwriting, claims, and customer service. AI's integration promises enhanced efficiency and accuracy. AI models can be employed to streamline and automate claims processing workflows. This automation reduces manual effort and processing time. AI algorithms can analyze claim data to identify patterns and potential issues. The system can assist in verifying claim legitimacy and processing payments efficiently. AI models can be leveraged to tailor insurance products. AI facilitates the personalization of insurance services. These AI applications enhance customer experience. Personalization leads to more relevant offerings. AI-driven customization improves customer satisfaction. AI models are increasingly used to detect and prevent insurance fraud. These models analyze vast datasets to identify suspicious patterns. The AI algorithms can flag claims that deviate from the norm. Predictive modeling helps anticipate potential fraudulent activities. This technology significantly reduces the time to investigate claims. AI-driven systems enhance the accuracy of fraud detection processes. Ethical AI practices emphasize responsible development and deployment of AI technologies. These practices aim to minimize potential harm and maximize societal benefits. Key considerations include fairness, transparency, and accountability in AI systems. Responsible AI development involves addressing biases in data and algorithms. Implementing ethical AI ensures AI systems are aligned with human values and legal standards. Transparency in AI models refers to the ability to understand how the model arrives at its decisions. Explainability focuses on making the model's reasoning process clear and understandable to humans. The need for transparency and explainability is increasingly important in AI applications. Understanding the decision-making process of AI models builds trust and facilitates accountability. Data privacy and security are critical considerations in the development and deployment of AI applications. AI systems often handle large volumes of sensitive data, increasing the risk of privacy breaches. Robust security measures are essential to protect AI systems from cyber threats and data manipulation. Implementing privacy-enhancing technologies can help mitigate risks associated with data processing and AI. Ethical AI development requires a strong commitment to data protection and responsible data handling practices. Continuous monitoring is essential for maintaining AI model performance. Ongoing evaluation helps identify potential issues and biases. Monitoring ensures the model continues to meet its intended objectives. Evaluation provides insights for model refinement and improvement. Regular assessments are crucial for responsible AI deployment. Effective database design requires collaboration among different specialists. Data scientists contribute their analytical and modeling expertise. Business users provide insights into data requirements and business processes. IT professionals ensure the database is technically sound and maintainable. Collaboration ensures the database meets both business needs and technical standards. A strong data governance framework is essential for effective database design. Data governance establishes policies and procedures for managing data assets. This framework ensures data quality, integrity, and security throughout its lifecycle. It defines roles and responsibilities for data management and usage. Effective data governance supports informed decision-making and regulatory compliance. Data literacy is crucial across all levels of an organization. It ensures that employees can understand and work with data effectively. This leads to better decision-making and strategic planning. Ultimately, data literacy enhances overall organizational performance. A data-driven culture emphasizes the use of data in decision-making processes. This approach ensures decisions are based on evidence rather than intuition. Organizations foster this culture by providing access to relevant data. Training employees to interpret and analyze data is also crucial. Data-driven cultures promote transparency and accountability. Ultimately, this leads to more informed and effective strategies. AI models can be leveraged to optimize pricing strategies. These models analyze market data to dynamically adjust prices. This ensures competitive pricing while maximizing profitability. AI also enhances underwriting processes by assessing risk more accurately. Machine learning algorithms identify patterns indicative of potential risks. This leads to better risk management and reduced financial exposure. AI models can be leveraged to enhance risk management strategies. These models provide tools for identifying potential risks. AI can assist in assessing the severity and likelihood of identified risks. AI algorithms are capable of predicting future risk scenarios. AI can be used to develop proactive risk mitigation strategies. AI-driven insights can improve the overall effectiveness of risk management processes. Data utilization is crucial for adhering to regulatory standards. Organizations must leverage data to demonstrate compliance. Effective data management ensure accurate reporting. Compliance-driven data strategies minimize legal risks. Database design is crucial for identifying potential business opportunities. Well-structured data facilitates the discovery of market trends. Analyzing data can reveal unmet customer needs. Effective database design enables efficient data mining. Data-driven insights support strategic decision-making. Identifying new business opportunities is a key benefit of proper database utilization. Continuous innovation is crucial for maintaining a competitive edge. It allows for the development of new features and functionalities. Innovation helps in adapting to changing user needs and market trends. It drives improvements in efficiency and performance. Ultimately, continuous innovation ensures long-term success and relevance. A clear understanding of business requirements is paramount in database design. Effective database design aligns with and supports specific business needs. Business requirements dictate the structure and functionality of the database. Ignoring business requirements can lead to inefficiencies and data management issues. A well-defined data model is crucial for effective database design. The data model provides a blueprint for organizing data within the database. It ensures data consistency and integrity across the system. A clear data model facilitates efficient data retrieval and manipulation. It also supports the development of robust and scalable database applications. Data types define the kind of values that can be stored in a column. Choosing appropriate data types is crucial for data integrity. Using the right data type optimizes storage space. Correct data type improve query performance. Selecting appropriate data types improve data validation. Proper data type usage ensures consistency across the database. Data validation is a crucial aspect of database design. It ensures the accuracy and reliability of the data stored. Proper validation prevents incorrect or inconsistent information from entering the database. This process helps maintain data integrity throughout the database lifecycle. Ultimately, data validation contributes to the overall quality and trustworthiness of the database. AI models enhance customer communication strategies. These models enable personalization of messages. Personalization tailors content to individual customer preferences. This approach improves engagement and customer satisfaction. AI models can be leveraged to enhance customer loyalty programs. These models provide insights into customer behavior and preferences. This enables businesses to tailor loyalty initiatives for better engagement. Examples demonstrate practical applications of AI in improving customer retention. Building trust with customers is crucial for long-term business success. Data plays a key role in establishing and maintaining this trust. Utilizing data effectively can demonstrate transparency and reliability. Customers are more likely to trust businesses that use their data responsibly. This involves protecting customer data and using it to improve their experience. Ultimately, data-driven practices can foster stronger, more trusting customer relationships. Strategic database design enables businesses to leverage data for competitive advantage. Effective data utilization can improve decision-making processes. Data-driven insights can reveal market trends and customer preferences. Competitive advantages can be achieved through optimized data strategies. A customer-centric approach is crucial in database design. This approach prioritizes understanding and meeting customer needs. Database structures should reflect customer data requirements. Focusing on the customer ensures data relevance and utility. A well-structured database is crucial for effectively leveraging AI in the insurance sector. Proper database design enables accurate predictive modeling for risk assessment and fraud detection. Efficient database operations streamline insurance processes, reducing costs and improving response times. A well-organized database facilitates better customer service through personalized interactions and tailored products. Therefore, database structure is a foundational element for successful AI implementation in insurance applications.